So let's move on to the next section. That's a student intern presentation, and I'll invite Ilse to start first.
Alrighty, can you guys see that?
Yes.
Excellent. So hello everyone and welcome. My name is Ilse Perez and I am a manufacturing engineer. And currently I'm working on my master's here at UTRGV. And I work at one of the laboratories here at the university as a research assistant. And today I just wanted to talk to you guys about a topic that I have had the pleasure of working with. And that's the topic of regenerative medicine. And we do that via coaxial bioprinting. And so just before we begin, I just want to let you guys know that if you have any questions or want me to elaborate on something, please feel free to go ahead and put that either on the chat or if y'all can speak, you can go ahead and do that as well. So during this presentation, I'm just going to briefly discuss what regenerative medicine is, show you a little bit about what bioprinting is, and finally show you guys some images that some of my coworkers and I have taken of the prints that we've done, of cells that we have worked with in the lab, and all of that. So, the previous presentation was about additive manufacturing. This is kind of, going off of that as well. Except here in this case, we're more on that bio side of additive manufacturing. And so regenerative medicine, I hope you guys have heard about this. If you haven't, that's also great because I get to introduce this topic to you guys. So what is it, right? So as you can see on this slide, regenerative medicine deals with the process of replacing, engineering, or regenerating human, animal cells, tissues, or organs to restore or establish normal function. So what does that mean? Basically, this just means that through regenerative medicine, with the technology that we have available, we're able to create these functional tissues, either from animal cells or human cells. So here I have two pictures. The image on the left, let me try to zoom in. This is an actual picture of the first vascularized heart in the world. And so this one is a very, very, very tiny model of a heart. So this one wasn't functioning at the time. I believe this was done in Israel, if I'm not mistaken. And then on this side, we also have another image, and this is a much more, I guess it's more similar to like an actual functioning heart. And this one actually was able to beat. And this was done at one of the laboratories at Harvard. And both of these hearts were created through different methods of bioprinting. And so in this case, we're using cells and we're using bioink. And so this is super interesting. This is actually, the future of bioengineering. And through all this research and experimentation, we can get closer to creating a lot of different types of functional organs. So let's move on to bioprinting. We already kind of talked a little bit about what bioprinting is, but we're just going to go a little bit more into detail and define that. So as we can see on this slide, bioprinting is a computer-aided layer-by-layer additive manufacturing process that uses biomaterials, such as bioinks and hydrogels, as a microenvironment for living cells for the creation of functional tissue. So once again, we see those words, bioinks, biomaterials, hydrogels. And so basically that's just material in a gel form that we use to print or 3D print, right? These tissues. And so at our lab here at UTRGV, one of our goals is to create vascularized tissue that can help us create a base for a retina. And we're currently experimenting with a process called coaxial printing, and we're just going to introduce that in the next slides. So here we see a little model of the retina. So as you can see here, this is like a zoomed, let me get the laser pointer. This is a little zoomed version of our retina. And all of these lines right here correspond to different types of cells, and they're all connected to form this, this part of the eye, right? And so that's what we're trying to achieve here at our laboratories through this printing. So 3D printing versus bioprinting, what's the difference? So while both 3D printing and bioprinting are a computer-aided layer-by-layer additive manufacturing process, 3D prints don't have that addition of cells in the prints. So let me zoom in here and we can see these different types of printing. So we have 4 different options. This is just the different types of 3D printing that we can have, you know, with either a single material, as you can see with the blue lines. We can have different layers with different materials, right? The blue and purple on the right. Then the bottom left corner, we have these different lines that are interchangeable. And finally, we have pattern lines. And so that includes even more materials. And then we also have this bottom part, which is more towards bioprinting. And so we have 2 options. We have post-seeding, which is basically adding cells on top of the printed layers that we've created, and bioprinting. So for post-seeding, we can use either just one cell type or different cells, which makes it multicellular. And then we also have bioprinting, which is basically printing with the cells. So as you can see, the cells are running with the print. And again, we can use that with one cell type or with different cell types, making that multicellular. And so this is all very interesting work, and this is what we're trying to achieve as well at our laboratories. And so how do we do that? We're trying to do that through coaxial bioprinting. And so if you guys aren't familiar with this, I'm gonna go ahead and explain that for you. Before I actually entered into research, I did not know how exactly coaxial bioprinting worked. As a manufacturing engineer, I wasn't as exposed to all the bio elements of this project, which makes it more interesting for me because I get to learn about all these different ways to work with different additive manufacturing processes and working with actual cells and bioprinting. And so this is the method that we use at our lab. Basically, coaxial bioprinting uses a coaxial needle or nozzle that's able to print using 2 different types of materials. And this gives us a tubular structure. And so as you can see in this first image over here, we have 2 materials, right? We have the blue that goes through the middle and the red that goes through the outside. And so we can see here that the blue material that goes through the middle, this is the needle that we would work with. So the blue material would go here with this gold outer needle or inner needle. And then we have the red material, which would go here into this feed tube and give us that outer material. And so you guys can kind of see the colors as well matching with this model. And that just basically putting those materials together, which are a kind of gel-like structure, but it's once that they are printed together, then when these hydrogels meet, that they have a chemical reaction and harden a bit to give us that jelly-like structure. So here, these are the images that I actually took from our lab. These machines over here, these are single syringe pumps. And basically we place our pumps on each of these machines with our different materials. And those syringes are attached to the needle, which is found here on this area over here. And this is our plate. And so all of this is controlled by our computer. Basically with our computer, we will determine the rate at which we want the material or the syringe to be extruded at. And then we also can choose with this base plate over here where exactly that's going to move, so we can manipulate where that material will be placed when printed. So these are also some other images that are taken in our lab. They show up, this is like a close look of how the hydrogels look during a print. As you can see, these are a blue dye. And we just did this to kind of tell to see if the 2 materials were mixing together. So you can kind of tell in this picture, the outside is more transparent and the middle is that blue dye. And so that lets us know that the needle or the nozzle isn't clogged and that we're able to do some successful prints. And so these in particular don't have cells in them yet. This is just a hydrogel. And we did that just to kind of explore what kind of ratios of our materials we needed to get that good consistency. And so both of these have different consistencies. And as you can see, the flow looks a lot different. This one's a lot less uniform than the one on the right, which is a lot more, I guess, uniform. And here we can see our printer in action. So this first video basically shows how the plate is able to move through the computer. And then here we see the two syringes being connected to our needle or our nozzle and the actual print. And so the second video shows us injecting some of the ink in the actual pathways. And this again is just to make sure that we're getting that, that little vasculature, right? And this is just so we can see if the liquid is able to stay within the boundaries. And that's part of the research that we do here. And finally, we have this other picture. These are just some of the materials that we use to create the hydrogel. In our lab, we use calcium chloride, sodium alginate, and collagen, which are our main materials for our gels. And we tested a bunch of different concentrations and combinations of these materials to get that tubular structure. And so moving on, these are some images that were taken with our Nikon fluorescence microscope at our lab. So this is an image of that microscope. And here we see the ideal bioink concentration that we found. And these are the tubules that were printed. And so as you can see, there's a very defined outer walls to it. And so this makes us see that it's a completely 3D printed structure and that it's the hydrogels are gelling in the correct way or in the way that we want. Okay, so here in this other picture, we actually were able to print with cells and observe how the cells reacted within the hydrogel. And so here, as you can see, there's these white circles, and these show how the cells have migrated from this internal point to the outside. And so that created these little channels in our hydrogel. And so these were also taken with our fluorescence microscope. These were actually dyed green to show a little bit more in contrast, defined, I guess, where the cells were going through. And so this is something very interesting that we also want to continue exploring and seeing just how those cells behave within the hydrogels. And so basically that's what we're working on at the moment. This is an image of our lab. This is a research facility. It's located in McAllen, Texas. Maybe you guys have seen it. It's over by Dove Road by McColl and Jackson. So if you guys ever want to drive by and see our facility, it's there. And here are some other images that I took throughout the internship this summer that I had while starting my work there. And here we just see some of the cells. We were making sure that they were nice and alive before we used the hydrogels. This is just a picture that I took to share with my friends of me doing some research, reading a lot of papers and all that. Here we have just an image of a centrifuge, and this was just to create or get our cell pellets. And finally, we have some of like our fume hoods that we use to create our gels. And lastly, we have this little video that I took one day where I was just going into work and I just kind of wanted to show one of the places where I like to sit down and do that research. And so here we see all these like other centrifuges, machines, a bunch of materials, and this is just basically where I sat down sometimes, to do that research. And just, I guess a bonus, I just wanted to show you guys some of the pictures when I first started working at the Biomedical Research Center. And this over here on the very left is my coworker, Rihanna, who taught me how to do all these work with these cells and everything. So that was very, very interesting for me to learn. And so just in conclusion, bioprinting is the future of regenerative medicine. And through these research and experiments conducted in the labs, we get closer to creating that functioning tissue and organ. And that's like very life-changing for a lot of people. And I guess with that, I just wanted to share again that UTRGV offers state-of-the-art equipment as well as guidance from professors that really help us learn and discover these new things. So if you guys need or want more information of our engineering programs, please feel free to reach out and we can get that information to you. And just some resources. But thank you guys very much for sticking with me through this presentation. And again, if you guys have any questions, please feel free to put those in the chat.
Thank you, Ilse. So Ilse is the graduate student in our biomanufacturing group, and she's the lead in the group. And if anyone has any questions, go ahead, send her an email to ask, and she'll be happy to answer. Right. Okay, so let's go next to Mary. Mary, go ahead.
Are you guys able to hear me and see my screen?
Yes.
Okay, so hello everyone, my name is Mary Pletcher, and today I'll be presenting on advanced manufacturing and machine learning, which are two topics that I explored during my iDream 4D summer internship. Thank you so much to my advisors, Ben Stanfield, Dr. Kong, and Dr. Lee. So today I will be going over a kind of introduction of me, give you a quick look of where I worked over the summer, provide some background information, go over the project that I assisted with over the summer, and then there'll be time for any questions if anyone has any. So as a short introduction, I'm a junior at Virginia Tech over on the East Coast side of the country. I'm majoring in industrial systems engineering and minoring in human computer interaction. Fun fact about me, trying to grow my plant collection, which I started over this past summer. And on the slide, you can also see some pictures that I took from my experience over the summer, some cool projects and equipment that I got to work with, and then also just some fun activities that I did while I was in Blacksburg. So a short introduction to where I worked over the summer. I worked in person at the Virginia Tech Learning Factory, and I worked virtually with Honeywell, the company, and the University of Texas, Rio Grande. So we were meeting over Zoom, and on the right here, I should be able to play a short video of the lab that I was working in. So you can see here, this is just some workspaces. In the background, you can see some sponsors of the lab. That's a camera that was being used for another project we were working on using these robot arms that are in the learning factory. And in the background, you can see other machines that are available at the learning factory here at Virginia Tech. And up here, you can see some 3D printers that are used in the lab. And then that table was really messy because the lab was being organized. And then finally are just some workspaces. But yeah, it was definitely a very interesting place to work over the summer, and it was fun to be close to so much technology and just interesting machines. So I will move on to the next slide. So just some background on some of the topics that I explored over the summer through my summer internship that you may or may not be familiar with. So first, advanced manufacturing. So advanced manufacturing is using cutting edge technology to improve manufacturing processes. It's really closely related to Industry 4.0, which is a term used to describe the fourth industrial revolution. And so Industry 4.0 is all about using data and machine learning to create smart and autonomous systems to improve industry practices and manufacturing processes. And then additive manufacturing, which I believe you guys got some introduction to in other presentations, but it's essentially printing a part layer by layer to create the final shape. So you start off with a 3D file, and then you basically split the 3D object into layers and use that as instructions for the 3D printer. And additive manufacturing comes in many different many different types, including metal, plastic, and cement. And again, I think you guys heard a little bit about these different types of additive manufacturing in previous presentations. And then finally, what is machine learning? So machine learning is a type of artificial intelligence that uses data and algorithms to imitate the way that humans learn. So as you can see on the right here, machine learning is a subsection of overall artificial intelligence that really focuses on imitating the way humans learn, which includes gradually learning and improving accuracy over time. And within machine learning, you have these phrases like neural networks and deep learning, which essentially automate that machine learning process. So it requires less manual human intervention to initiate that learning process. And this allows for larger data sets to be used and even more relationships between the data to be learned. So essentially the computer is training itself how to learn like a human would learn. So the project that I helped with over the summer was machine learning error prediction for closed loop additive manufacturing systems, which is a mouthful, but essentially it was using machine learning to predict errors that would occur during the additive manufacturing process. So the overall objectives of the project were to contribute to closed loop error compensation systems for additive manufacturing. So on the left here, you see an example of an open loop system, which would be taking printing parameters like the part shape, the layer thickness, the extruder temperature of the additive manufacturing machine, and then you would print the part and then you would test the part to see if it met the qualifications. But a more effective way to do additive manufacturing is through closed loop systems. So you start with the same printing parameters, you would collect data, process the data, and then you would do some type of error prediction or error modeling and use that model to do error compensation, which then updates the printing parameters and minimizing the amount of error that occurs during the printing process. So the question was, how accurately can machine learning predict part shape and part surface for the fused deposition modeling process? And fused deposition modeling is just a type of additive manufacturing or 3D printing. So the goal was to have an ideal file of what the part would look like. That's called like the STL file, the designed part. And then a neural network would be used to predict the actual printed part shape. So in order to achieve this, both a whole bunch of STL ideal part files and data on the final part shape, as you can see on the right, are needed to train the neural network to learn the relationships between the data from the initial part file and the data from the printed part file. And so in order to train a neural network to learn these relationships, there was data collection that took place. So 10 different parts that were each slightly altered were printed out, as you can see here. And so the goal was to have those design files for these printed parts, and then to print them out and then 3D scan them, and then we would have the data of the final part shape. So here's a picture of me doing some 3D scanning. And on the next slide, so after we collected all of this data and printed all of these parts, the next steps were to clean the 3D scan files and then match the initial STL print file to the 3D scan file. So here's some images of me contributing to that part of the process. And both of these steps were necessary to create data that could be used to train the neural network that was clean enough and only contained the valuable information for the neural network to learn the relationships between the before and after of the part. So neural networks use different layers to learn the relationships between data. So this is the layer structure that we used for the neural network. So it was a 24-layer convolutional neural network, which is a type of neural network. And so each of these layers contributes to that learning process. And so after feeding the training data that we had collected, the goal was to then test how accurately the neural network could predict what a final part shape would look like. And so here are the results. There was a 97% total shape accuracy. So the neural network was able to be 97% accurate when predicting what the final print would look like. However, there's only a 6% accuracy of the surface. So when looking specifically at the surface features of the printed part, the neural network was far less accurate. And so while the 97% total shape accuracy is enough to be used for error prediction, the 6% surface accuracy indicated that more work needs to be done to improve the accuracy of the neural network and to make it more useful for error compensation and error minimization processes in the future. So beyond improving the neural network, some future work is to eventually develop a whole closed loop additive manufacturing error compensation system. And then in this realm of additive manufacturing error compensation in situ or during the printing. Error compensation is something that is also currently being explored for additive manufacturing. So I learned a lot from this internship. You saw at the beginning of my pictures, I had a great time. I was basically learning something new every single day. I was expanding my technical skills, programming, learning more about 3D models, 3D scanning. I had the opportunity to understand some of the project management side. And I overall had a great time connecting with people all over the country. I got to talk to interns all the way down in Texas and communicate with Honeywell people as well. And so that was a great time. And so these are some sources, but I would also be happy to answer any questions and also put my email in the chat if anyone wants to ask questions about Virginia Tech, the work I did over the summer, or just engineering in general. I'd be happy to share.
Thank you, Mary, for sharing the internship experience. That's excellent. And actually, Mary is an outstanding intern student in the summer. And for the internship opportunities next year, I will give more information in next section. Mary should leave her email in the chat box so you can ask questions directly to her. Okay, thank you, Mary. So next one, Shawn, are you ready?
Yeah, I'm ready.
Yeah, go ahead. Mm-hmm.
All right, so good afternoon, everybody. My name is Shawn Hatcher. I am a graduate student here at Mississippi State University. And we're going to take a little bit of a detour away from the DoD, but we're just going to talk about additive manufacturing. I'm really going to talk about the DOE project that I'm funded for right now, but use the iDream 4D consortium to support me for my additive manufacturing research. And so today we're going to talk about the engineering next age of solar power, but we'll be using simulations and 3D printing to produce the solution for a climate crisis as well. So just a little overview of the presentation. We're going to talk about what solar power is and how the climate crisis is affecting us as a society today. Background knowledge. We're also going to do some simulation results and 3D printed models that I did over the summer. And then finally, we're going to finish with a conclusion. So why are we concerned about the climate crisis? Well, to quote the UN directly, the last 4 years were the hottest 4 years on record. The increase in temperature has been absolutely terrible for the ecosystems, polar ice caps, and then the weather has been increasingly worse, as we saw with Hurricane Ida and the forest fires the past couple of years in California and such. Also, with 2/3 of the world's population living near these sea borders, it's going to be a major concern with rising sea levels to control and limit that as well for society as a whole. So there's some new extremes also going around with climate crisis. There's 90% of disasters are classified from the climate related, but also there's a bright side. There's going to be a new path forward, and I'm going to talk to you about that, how we're marching with that right now. Renewable energy is becoming cheaper and cheaper. In some places it's the cheapest option, which is fantastic to understand. Also, electric cars becoming more and more popular, obviously with Dr. Lee this morning talking about a certain someone. So I believe the electric cars is going to be a good futuristic and alternative option. But so why are we focused on solar power, and what is it exactly? So solar power is the energy from the sun that's converted into thermal or electric energy. Also, solar energy is the most abundant renewable energy source that we have in the United States. As you can tell in this picture on the right here, this is demonstrating the solar concentration throughout the entire US. As you can tell in the western half of the United States, it has abundance of sun with also a little weather to stop it. But also there's 3 ways to collect solar energy. Photovoltaics, which is your typical solar panels that you would see, solar heating and cooling, and also concentrated solar power. The concentrated solar power is the focus of our project right now that we're studying. So let's just talk a little bit more of that. So what is concentrated solar power and why is it important? But before we get into what it is, there's 4 different types. There's a parabolic dish, parabolic trough, solar power tower, and the linear Fresnel. We're going to be talking about the solar power towers, and these power towers offer a high efficiency and an ability to store the energy that they produce. This is very important concept to consider for solar power, as most solar panels are not able to store energy. They just use it directly. The high efficiency from these power towers is produced by an intense focus of sunlight onto one spot of a receiver, which is then inducing a high heat, which is going to then produce some steam or some heat generation into a fluid, which is in turn, as you can tell, to a steam drum, which then goes into a turbine here in this picture on the right, turns to generator, turbine turns to generator, and then the generator produces electricity. Also, the generator can store energy as well. But continue with the storing energy, this is one of the, like I said before, big positive for CSP. Typical solar panels are not able to use stored energy. They use it directly because CSP uses mechanical power to generate the electricity from the heat transfer fluid. It's able to store some of that extra heat, which is nice. So what do these power towers look like? These pictures right here are just a few samples that I found on Google Images that showcase how the CSP solar power towers look in the industry. So the title of my presentation, we're using simulations and 3D printing. So first off, what are simulations and why do we use them? So first off, these simulations that you see on the slide, the 2 left are not from my own doing. I found them also on the internet. So we're not focused on turbine planes or airplanes, but however, just to go further, the definition of a simulation is the production of a computer model to do something, to solve for something. That could be in the animation in the upper left, that could be for velocity, or in the lower left, that's streamlines, for instance. This is going to solve for something. And so the computer simulation uses boundary conditions that are applied to a computer-aided design, a CAD drawing, to calculate these results. And so these results in our project that we're looking at today are going to be some temperatures, some velocity profiles, and some stresses. And the CAD picture is a sample, is this lower right picture here. This is a CAD drawing that drew myself in SolidWorks to showcase our effective design for the solar absorber tubes. So why do we use these simulations? Well, we use the simulations to save the time and money for projects. As we discussed earlier in previous presentations, if you have a prototype that's 3D printed, you're using time to make the product and then also implement it into a test chamber, like a wind tunnel or such. And so that's going to take more time and money as compared to computer simulations. If you set your boundary conditions up correctly, you can yield accurate results and without having loss of manpower or time in a project. And so how do we produce these CAD models? We have a slew of options to look at, as we saw in Paul's presentation, but I'm particularly going to talk about a selective laser melting, which is also known as a powder bed fusion. So selective laser melting is a manufacturing process that uses powder bed of metallic material that is heated by a powerful laser to build a part layer by layer. As you can tell in the left GIF and the right GIF images, you can tell by the laser being shot into a mirror, and then the material being formed from the laser, also then the powder going over the top of it and being formed again. So this allows us to make some complex geometries, such as our solar absorber tube with the high aspect ratio fins and thin layers as well. Since these are also in a powder form, the materials in a powder form, more or less, the mixture of any kind of metallic compound you can make rather easily just with some mixing processes. So you can have a very customizable hybrid type material that can be made at a very specific geometry for the particular application you're looking for. And so here are some 3D printed models that we did over the summer. The top 3, A, B, and C, are made out of PLA material, which is just basically plastic. Actually, I have the piece right here. Actually, I'm holding it. It's only about 3 inches long or so. But these three different designs are what we just considered over the summer to potentially have for the Solar's over tube to have a higher efficiency value, because as I show in the next slides, I'll discuss the difference from a fin design and non-fin design. But also, you can also see that in the bottom two pictures, we had some 3D printed samples from UTRGV lab that we collaborated with this summer as well. Those are made out of a stainless steel material, and they follow the Delta fin design. That's the B in the upper pictures, as you can tell. What software did we use and what boundary conditions did we apply to this particular system? So the software that I used this summer was COMSOL Multiphysics. COMSOL is a simulation software designed with real-world applications. COMSOL offers a user the ability to implement different types of physics into the model. This could be heat transfer, a fluid flow, mechanical stresses. COMSOL also offers electricity, acoustic, radiation, just a lot of real-world physics that you can put into your model at an relatively easy scenario. Also, COMSOL allows these physics to be coupled together. So, for example, you could have a turbulent flow inside the pipe, as we're going to show here in the next couple slides for simulation results. There's going to have an inflow from the heat transfer fluid, but this flow is going to be different. It's going to have some low velocities, high pressure, and high pressure, high velocities, low pressure, and so on and so forth. And it's going to be coupled with the heat transfer to produce an accurate plot of what the temperature distribution is going to look like in the system. So just a little set of boundary conditions that we did for the system. This is going to be a 3 meter long length tube with a 1/2 inch diameter. So it's going to be a really small, thin tube, as you could expect. Some initial conditions: the inlet temperature for the heat transfer fluid is going to be 500 degrees Celsius. The amount of helostats, which is the mirrors focusing onto the one Solar's over tube, is 500. So that's going to greatly increase our temperature focused onto the pipe itself. And the inlet velocity is going to be 4.5 meters per second. So here are some results that I gathered through my summer internship with COMSOL Multiphysics. The picture on the left is going to be the fin tube, and the picture on the right is a finless tube. And as you can tell, the picture on the left has a more temperature gradient friendly plot. As you can tell, it goes from a dark blue to a medium, or not dark blue, a dark red into more of a maroon, then to a red, orange, and a yellow. This is due to as I said before, the fins causing the rotation, and coupled with the heat transfer is going to actually have some temperature values, and that's what COMSOL saw for there. The thermal efficiency for this particular design was 84.24%. Now compare that to the finless tube on the right. This has no fins, and it's just a very typical slit tube pipe. There's no internal geometry at all. As you can tell, there's a really high max temperature of 739 degrees Celsius, which is caused by the helostats focusing the sun onto the tube itself. And the minimum temperature is 549 degrees Celsius, which is what the inlet boundary condition was. So that yields a difference of 109 degrees Celsius as compared to the 8 degrees Celsius difference from the fin tube. And so as you can tell, it's not as effective as a thermal efficiency of 76.4%. But also, since there's a great difference, there's a huge difference in temperature values there, you're going to have a lot of thermal stresses, and you're going to have a lot of oxidation and other corrosion values happening on that one edge because it's so much hotter compared to the other surface as well. So that's what we're trying to limit here, and essentially is to have more even temperature distribution through the system. So here are some velocity plots that I accumulated from the simulation results. As again, the one on the left is the fin, and the one on the right is the finless. So as you can tell, there's something different happening here, obviously, between the two geometry files. So the one on the left has a higher max velocity of 6.89 meters per second, and compared to the finless of 5.34. The finless follows a traditional velocity profile as you would have a parabolic curve coming around for a finless section, but as opposed to the fin section, it does not follow that, and that's because it has rotational and axial flow through the pipe. But you also may notice that there's a lot bigger band of zero velocity or very low velocity for that matter. It might not be zero, but it's very low. So this is also a concern for us with corrosion inside the pipe because of there's no fluid flow in there. It is causing some buildup, and they potentially have some problems in our system. But nonetheless, my time with the research for the I4G for the I-Dream4D consortium was a lot of fun. I had a great time. Here are some pictures from my campus, Mississippi State University. The picture in the upper left is our research team here on campus. We are the multi-phase transport lab. We are actually in SWAM, which is the picture in the middle, bottom middle right there. Picture on the bottom left is our lab. However, the picture on the bottom right is a picture from that building where our lab is taking place. It overlooks our famously known drill field. So it's a very beautiful campus, very beautiful lab, and a very great support group. But I also had a great time with the consortiums this summer, and highly recommend it. So just to conclude real quick, there's going to be some drastic need for engineers to look towards the future for more renewable energy. And so we can decrease our carbon footprint and kind of limit the weather extremes that we have so far. A main way to do this involves solar energy. It's very abundant in our country, obviously. To that picture I showed you at the beginning of the presentation, we have a great opportunity to exploit that resource. A highly efficient type of solar power is with the CSP, the concentrated solar power we talked about in this presentation, because it has the ability to have high temperatures, which is allow greater efficiency through mechanical to electrical transfer, and also the ability to store the energy from the generators. Simulation and SLM processes lower the overall cost of projects due to the decrease in material wasted and time to produce the results. So that this is the whole National Manufacturing Day is very good for our industry, because obviously we're going to be saving time and money, and everybody likes saving time and money. Also, implementing an internal thin structure, and this increases the efficiency of the solar absorber tube. And the structural issues are decreased because of the evenly distributed heat throughout the system as well. So thank you for all that, and here are my references. And I'm open for any questions. Like everybody else, I put my email in the chat. If anybody wants to contact me about Mississippi State, the Bagley College of Engineering, mechanical engineering, anything, I'll be glad to help for sure.
Thank you very much, Shawn.